Okay, here we are in the lab again. And so this is episode number 10 of Build Your Own Main Brain Microcontroller project. And so in the previous video, we covered like PPS and IO ports and stuff. But I wanted to mention one thing to add to that, and that's like the microchip development environment, or the IDE, their compiler XC32. When you type in like port in capitals, the header file automatically detects that, and it highlights it as a register, so that you can just type port C and you can write to port C. So then also, in addition to that, you can add bits, B-I-T-S, on the end, and then hit a dot, and that will bring up a little menu where you can select the bit that you want to write to for bit manipulation. So turning bits or pins on and off. All right, so that's an important feature that's only for the microchip development environment. If you try to use that same code, if you pull it over into Visual Studio and it's not set up properly for the microchip stuff, then it won't do anything. It won't work right. It won't know what you're talking about. So let's jump over to some code, and I'll explain how they implement that in their header files, and then we'll take a dive into how we use the peripheral main port to develop a data bus and an address bus. And then that's pretty much it for the interfacing. Then we can start doing some real firmware and write some device level code and some device drivers probably in the next video. I think that's probably next. But right now we want to set up the PMP, the Peripheral Master Port, they call it. And that way you can interface with the data bus and an address bus and a read and a write and a chip select to various chips. Like on main brain, I do the flash, the SRAM, and the display are all on the same data and address bus. And at 16 bits, you can have 8 or 16 bits and up to 16 address lines. All right, so let's jump over and check that out. Okay, so here is, for instance, TRIS-G. So that's our tri-state register for port G that sets up whether we want an input or an output. And so it has this bits added on. So let's take a look at how they do that. They also have port D, and you can put bits. So when you do the bits, that means that you can select a single bit in that port. So let's take a look at how that is implemented in their header file. It's called a macro, and a macro is a definition that replaces text in your source code before the actual compile. All right, so let's jump over to a fresh page in Visual Studio. So basically, it's what they're doing is this. So let's get this thing down here out of the top. Let's get it down here a little bit where we can see it. All right, so this is basically the way they do it. So they define port C as being this here. So anytime you write port C, when it gets compiled, it actually does this. So it creates this as a memory pointer to this address. But this isn't the real address. This is just an example. They use the special function set, register set, and it's a larger address than this, but this is a good example of how they do it. So they define it, port C as a pointer here, and it's an unsigned character, which is 8 bits. And the volatile, it has to be volatile. So the reason that it is critical to be volatile is because the value it tells the compiler that the value can change at any time outside the program's control. So you must always read and write it exactly as written. All right, so this is how port C is defined. So then, in order to define the individual bits, you create a structure of the individual bits. Now, define a structure of the bits. So here's a structure, and these are all unsigned. Each one is 1 bit. So you got all your 8 bits for your 8-bit port C. And this is what it's called. But then they overlay the structure over the same address as up here. All right. So you end up with this like that. And so when you type port C, you get this address, a pointer to this address. And if you type port C bits, then you can access these individual bits by going. And with the defined, you can do port C equals OX, say 45. All right. So that puts hexadecimal 45 in port C. All right. But you can also hit individual bits, port C bits dot RCO, or whichever bit you want, equals 0 or 1 or whatever. All right. So that's how you would do that. And this is only for the microchip compiler. You notice this doesn't get highlighted as any kind of command or anything in here yet. All right. So let's go back to our microchip code. Okay, so in the microchip environment, when you type port G or whatever port you're talking about, it gets highlighted as a register like that, equals OX45. All right, so that would put 45 in port G like we were talking about. But if you want to, to do the bits, then you just add the bits part, and it doesn't highlight as a register, but when you hit the dot, then you get the selection for the structure. Oh, and yeah, I said 8 bits before, but these registers are 16 bits. My mistake. 16-bit register. All right, so so bit 0 through bit 15. But this particular register, you see some are missing. So port G, the higher ones have some bits missing due to their pins being used for peripherals or whatever. So, but if you go, let's try port A, bits. Oops, I better like spell it right, huh? Bits. Then you get 7, this missing one for A as well. Let's try this. Let's do it again here. Yeah, so there's some missing. There's in port A as well. So let's try port B, bits. And this one looks like it has all of them. All right. So it just depends on your how many pins on your device and all that stuff. But anyway, that's how that works for the ports. So now you know how to address the port or load the ports and individual bits. Okay, so now let's take a look at how we set up the peripheral main port and get ready to interface to the real world parts like SRAM and flash and displays and whatever else you can think of. Okay, so there is our data sheet, and this is the chapter on the parallel main port or master port. But I don't know why in their data sheet they're calling it the parallel host port, but it's the PMP, and they refer to it in their more specific data sheet, parallel master port. All right, so I'll call it the parallel main port or the parallel master port. So it can be 8 bits or 16 bits wide, and it is basically a port that creates a data bus, and I use that in MainBrain. That's in 16-bit dual buffer mode, and that interfaces with the SRAM chip, the flash memory, and the display. All right, so the display is 18 bits. So we use the 16 bits of the PMP plus 2 bit banged port bits, which I haven't really implemented yet because 16-bit color is still pretty good. All right, so, and that's what it says. It's made to communicate with like LCDs and external memory devices and stuff, just like I'm using it. And so you could use like an 8-bit port, but the thing about this is it includes your read and write. So, and also chip selects. Although I don't use that function, you can use it for 2 chip selects. All right, for 2 devices. All right. So you can also use it for multiplexed mode, like 8088 stuff, where you have multiplex data and address bus multiplexed together, and you have to latch at certain times to separate the address and the data bus. But I don't use that. I just use port bits for the addresses. And, well, actually not all of them. You can have a 16-bit address that you can generate from the parallel port. All right. So the advantage of using the parallel master port is that you get 16 bits of data, and there's on a separate data bus from the address bus, and you get up to 16 bits of address. And you also get chip select signals, 2 chip select signals, which I don't implement. And you get also the read and the write strobes. So when you write to the parallel main port, then it writes data out onto the bus, and it sends the proper signals. And you can change you can program the polarity of your chip select and your read and write strobes for active high or active low, however you wish. So that's the advantage to that. And you can see here they show an example of a buffer and an LCD and stuff like that, right? An external flash. And that's pretty much like I have. That's the basic idea of how MainBrain is designed. All right. Okay, so here is our list of registers to configure and control the parallel main port. And you can see they have parallel host port on this part of the data sheet. And so You got PMCon, which is the main control, and then this sets the mode, and this sets your addresses that you're going to, your port pins, port bits that you're going to configure as the address. All right. And then this is PMD out, PMD in for your in and out buffers. And then that's your address enable. You got some status bits here. This is you set up your address in here before you read or write. You tell it what address. And there's a write address and a read address. And then there's another register here called the read in. So it depends how you have this set up, whether you have it set up as legacy mode or dual buffer mode, of which ones you use. All right, and we'll go over that. So that's the registers that's involved. So let's take a look at the setup code that I have for our main brain. All right, so here is my setup code for the PMP. And I include this processor specific file because that's the processor I'm using. So you would want to, you could either use what is that one? XCH. You could either use XCH or you could use this one. This is more specific to the processor. That's just a header file that helps some of these commands show up. And so this is my initialization here. So the first thing you want to do is reset the module by turning it off. All right. So this is your PMCon register that we've seen in the list. And you just add the bits, suffix, and then dot on equals 0 or 1. And so not all of them are like that to turn them on. And some of them you have to put on or off. And if you define on or off somewhere else in your program, it can cause some problems. So be aware of that. And so then it's what I do here. This is the address multiplex. It means there is no address multiplexing. And so this PMP TTL SMIT trigger, no, don't need that, but you can. A SMIT trigger is good if you expect some noise. And so then we're going to use the write enable and the read enable strobes. All right. And then I am not going to use the chip select option either, and this one also, 1 and 2, 0 and 1. All right. And then so in this particular case, this sets up the active low. So this sets active low, 1 is active high for the write and the read. Normally they're active low, but you never know, you might want active high. And so then I'm setting the double buffer mode to on. All right. And so then the mode register, we're doing no interrupts. And so you can, anytime the port changes, you can generate an interrupt. And you can set this auto increment to where you read it or write to it and it increments to the next address. So you could just do like a loop where you're just reading it into a memory buffer, just and then it'll increment the address each time. And you could go through a lot of addresses like that. You don't have to set up the address or nothing. So that would be a speedy way to do it. But in this case, we're not going to set that right now. And you can set it on the fly too. A lot of these you can just set on the fly. Some you can't. Some you must set when the module is off. That's why you turn it off first. Then you do the configuration. All right, and that resets it too. So if you want to reconfigure this later in runtime, then it will reset it for you. All right, so then we don't automatically increment the address. we're in 16-bit mode. You can do 8-bit or 16-bit. So we're in 16-bit mode. So that means we're going to read and write in 16 bits each time. And then there's the different various modes. This is mode 2. And master mode 2 is what we are operating in here. And that is set here in the PM mode, parallel port mode register. All right. And so there is a busy bit for host mode only. It can be a client or a host, slave, whatever you want to call it. The actual mode is set here. So you got host mode 1. So you have the chip select, the read write, the enable, PM enable, and PM address set up, and the PM data. All right. So these upper data pins are not active unless you're in 16-bit mode. All right. And so then you have host mode 2, which is you got the chip select, the read and the write are separate. Up here they're like 1, and there's no enable. But you have your addresses and you have your data bit set. And so that's host mode 3, or well, actually the 3. That's how you set host mode 1. Host mode 2, enhanced client mode. So these are host modes. All right. So it's driving the bus. It's the boss of the bus. Now in client mode, it's pretty much controlled by the bus. And so you got your read and your write separate, your chip select, data, and address. All right. But the address is only 0 and 1 bits. And this is only bits 0 and 7. So there's no 16-bit option for client mode. And then you have legacy parallel client mode, which is basically the same thing, but there's no address lines at all for that. So that's how you determine what mode that you want. So we're using, in the example, host mode 2. All right. And so then there is one more thing we can cover here. Is that in there? That's down here. So then there's some wait states. Now, some memory devices, and even almost any kind of device, if you are writing at a very high frequency, you could have to put in wait states in here. So if we go back to the example code, okay, so there's our master mode 2. And so then this is our wait states. So this is the read, write, data setup wait states. And so we have one wait state here. Now, the read, write, data wait state is, I have set at 15. And it seems like a lot of wait states, but it makes it a lot more stable, and you'll just have to experiment with this because it depends on what kind of device you're writing to. And you can change this on the fly too. So when you go to write to a slower device, you can set it like this, and a faster device, you can lower this number and set this prior to reading and writing. And so then the data hold can be 0. All right. So this is the setup I'm using, and that's the most stable and fastest I can get away with. All right. All right. So then we're not using the chip selects. And so then this is how you set up the address bits. Okay. So this is the port pin enable register for the addresses. So the upper bits are not even implemented because this is a 32-bit register. But so this enables your strobe for the chip select 1. And then this is the address port enable. So this tells you if it's a 1. So in bit position 0 would be address 0. So if you just had 00001, then that would be for enable for address A0. All right. And then that's how you set enable the bits is right at 1 to that location. All right. So from 13, PMA 2 to 13. All right. And so then for the lower bit down here, it can function as latch high or latch low for your address, like on the multiplex stuff. All right. And the use of these pins as PMA1 or PMA0 or the latch depends on the address data multiplex mode. So, and that in the multiplexing mode, if it's the multiplexing is enabled, it operates with this, and if it's disabled, as in my example, then it operates as an address pin. So we want address A0 all the way up to A15. All right, so we get our full 16 bits, and then we have to bit bang other bits all the way up into, I believe, 19. All right, so if you can see that I am enabling all these address lines. So that is 16, total 16 address lines. All right. So then I have my chip selects are bit banged with just port pins. And so, for instance, port A, bit 9, is the chip select for the display. And RA0, port A0, is the chip select for the dual port RAM. And port A10 is chip select for the external flash. Now that we have it all set up, we enable the module and we're ready to read and write to it. All right. So then, since we're in double buffer mode, let's take a look at exactly how we read and write to it. Okay, so here's the function to read from the SRAM, the dual port SRAM. All right, so you supply a address. All right, and then so it comes down here, it just sets a bit that the SRAM is busy in case another function wants to read or write to it. You can't allow it to. All right, so then you get the data. So you do the PM R address, and you set your address, which is passed to the function right here. All right, and passed into the function, I should say, I guess. And then we set our chip select, so we select that chip, the dual port RAM. So now you have to do a dummy read to clock the data into the buffer. That's just the way it's built. The hardware is built. Nothing you can do about it. It's only for reads. Writes you don't have to, but you have to do a dummy read to clock the data in, and then you do your real read. All right, and you have to check to see if it's busy. If the PMP is busy doing something on a previous action or command, you wait for it, okay? And then you can do your dummy read, then you wait for it to complete, then you do your real read, all right? So you read the data into the PM read in. Now this is the incoming buffer for dual buffer mode. For a single buffer mode, this will not be the right register. All right. So then you deactivate your chip select, and then I return the data, which is 8 bits. All right. All right. So then the write is basically the same, except you pass the address and the data into the function. And so you have your address here, set your address. And that activates all your selected address lines for this particular address on your address bus, right? All right, so then we select it, the chip, the memory chip, and then you wait for the PMP to not be busy, and you send the data out. And then since I did the data out, I also wait for it to complete just to make sure. And then this is a thing I use to check to see if another device is reading and writing to the SRAM, and that's another subject later. All right, so now we're done with it. So we set the busy signal as false and deactivate our chip select, and we're done writing to the SRAM. All right. And so that's about it that's how simple it is. Oh, and when you write data out, you move data from the PMD out into your buffer. All right. Well, yeah. You're moving data from your buffer into this register, which puts it out on the bus. All right. And you notice PMD out is different than the PM read in. All right. So you have to pay particular attention to that, or you will not have a proper operating function. Okay. Okay, so now one more important thing we must consider is the actual pins themselves that will interface to the external devices, like the memory chip and the flash and the display and all that. So it depends on your particular package, how many pins, and what kind of package it has. And so you have to look at your data sheet here. And this is the pin definitions, right? We went over this before. But if you look, some of these definitions have like PMA5, okay? So PMA5, that's the parallel master address 5, all right? So that's, I enable all 16 address lines, so I will be using that one. And then you can see here's a PMD5. That is your data bit 5 from your parallel master port, okay? And you have to go through and see once you set up your master port, you can't use these port pins or the analog input or these other functions because that is your data and address bus, all right? Now you can disable it and do some other functions and then re-enable it on the fly. But once the PMP is enabled, you're committed to using this as the data bus, and you cannot use these other functions. All right. So then you got PMD 7 and 6 and 8, address 12, and here's your PM read and write right here. And it just goes on down. It skips around a little bit, but you will see that's where you pull your address and data bus pins off your chip. It's by looking up these pins on the device. So that's very important too. All right. And like here's PM chip select 1, or it could be PMA14. All right. So then you have to make a decision there. That's one reason I don't use the chip select feature. I need all my addresses and I need all my datas. 16-bit read and write with 16-bit 16 address lines plus. All right. Okay, there's the parallel main port and master port, parallel master port, or the host port, depending on how you read the data sheet. So You can see it doesn't take a lot of code to set it up. So, and it's highly configurable for your application. So different 8-bit, 16-bit, read, write, chip select, however many address lines you want, single buffer, double buffer. It's the engine for your superhighway going across your board, your data bus and address bus, and part of your control bus. And so it's important to get that worked out in your code and how you want it. And then you can worry about interfacing to just about any kind of chip that you can think of. Even if you want to interface with old 5-volt parts, the PMP is 5-volt tolerant. So you can interface directly to 5-volt parts if you want to. And there's a lot of different lines on the PIC that you can do that to. But anyway, that's it for today. That's it for this video, and I will see you in the next one.